Hi, my name is Naomi, and this is my motion of a falling object lab report. Some of the forces and formulas in this observation are from Newton's second law, such as the velocity update and position update formulas, and the forces involved were the weight force and the drag force, which have a summation that equal to the net force acting on the motion of the object falling. And for this lab, it's key to understand how these two forces, weight force and drag force, affect the motion of the falling object, and they must also be taken into consideration with Newton's second law in order to predict the falling motion over time. And the results from my data show a negative parabolic progression, and this negative progression is in the y direction and is due to the weight force being a product of gravity, which has an acceleration, and the drag force model from predicted shows different from the actual because our predicted drag force coefficient was estimated. For my tracker video, I chose to observe the motion of the falling object between frames 57 and 77, and the total time was 0.667 seconds, and I used my height as a reference for the distance of the falling object, and that reference was approximately 1.5 meters. And as you can see from the data in the table, but as well as in the graph, there is an acceleration of the object as it is falling due to the gravity from the weight force acting on the object. This acceleration is apparent as we are graphing the position versus time. In order to further understand how the weight force and the drag force are impacting the motion of the object, I graphed the comparison of the actual data versus the modeled data, and the two model data sets were the motion of the object affected by just the weight force and the motion of the object affected by both the weight force and the drag force. Some important observations to make about the graph is that the actual versus the modeled data for the data that included weight force and drag force are relatively close, but the modeled data is slightly beneath the actual data because the drag force coefficient was estimated. And you can see that the model data for just the weight force is significantly steeper than the other two because the weight force doesn't have to counteract the drag force. As a result, with just the weight force, the object falling should fall further quicker. For my code, I made sure that the initial conditions stayed at 0 because the object is falling from rest, and that the delta t matched the time steps of the tracker data. And I also made sure that gravity was equal to 9.81 meters per second squared, and that the j-hat vector was a positive 1 because it will later be changed to be negative depending on the situation. And the drag force coefficient was estimated to be 0.0097, and this drag force coefficient is used later in the code in the drag force equation. Overall, this code is supposed to help us predict the motion of the falling object using our forces and formulas, and to compare that data to the actual data in tracker in order to better understand how weight force and drag force affect the motion of this falling object. For more of the edits that were important to making this code a good model for this situation, some of the additions to the while loop were the addition of the weight force and the drag force formulas, and as well as their summation to calculate the net force acting on the falling object, and again, Newton's second law in the form of the velocity and position update formulas. Also, in order to make the visuals more apparent in the coding simulation, there were edits made to the arrow scale and which forces the arrows were representing. To answer the what does it mean question, when looking at the velocity versus time predicted by our models, it is clear that the terminal velocity can only be determined from the models that include both the drag force and the weight force. As you can see, by comparing the two velocity versus time graphs that model the motion of the object with and without drag, it is apparent that the model without drag does not clearly indicate when the object stopped accelerating, which is necessary in order to determine the point at which the object reached its terminal velocity. To answer the what-if question, when comparing the two velocity versus time situations in which the initial velocity is equal to zero and the initial velocity is not equal to zero, the terminal velocity would remain the same because in both models, the terminal velocity depends on the drag coefficient, which is remaining the same. Overall, this lab observation helped us to better understand how the weight force and the drag force affect the motion of a falling object.